Hi, good evening, everyone.
Good evening, sir.
Good evening, sir.
Okay, how are you all?
Fine, sir.
Should you all do revision of geological time scale, which I had sent in the group, that PPT. There were some questions also in that PPT. So, did you all do revisions? Okay. Have you all understood about geological time scale?
Yes, sir.
Yes, sir.
Okay, good. Okay, 7 people are there. Ask your friends to join fast. If you have their number, ask them to join fast. Okay, no issues. If they want to join, they can join in the middle. We'll start our session today. So yesterday we studied about the geological time scale. So today we'll start with continental drift theory. Then we'll study about convectional current theory. Then seafloor spreading theory. Then paleomagnetism. See, if you study all these 4 theories, then only we'll be able to understand about the plates and how all those movements are happening, and how mountains are created, how ridges are formed, how trenches are created. That will be understood only if we understand about this continental drift theory, convectional current theory, seafloor spreading theory, and paleomagnetism. For all these 4 theories that has come in modern times only, but in ancient times only on the basis of assumption they were trying to give theories, but that time no theories were given officially. But in 1920, that time continental drift theory was given by Alfred Wegener. Not in 1912. That time continental drift theory was given by Alfred Wegener. The continental drift theory was given by Alfred Wegener. In this continental drift theory, what happened? In early age, like in 1596, a person named as Alfred Walnus, he first used the term drifting. He saw that continents, mostly among all the continents, see, all this Europe, North America, South America, he saw that they have the rocks of same age. So in South America or Africa, so in that both continent, in this eastern side of South America and African side, western side of Africa, both sides the mountains, they are looking like a series, and they have the rocks of same age. So that first time he used the term drift, but he did not gave it officially, but that officially it was given by Alfred Wegener in 1912. So first, when he was traveling, he saw that all rocks of same age were found in some other continents also. Then some animals, some fossils were found in some 2 continents of same age. So in that way, he found the continental drift theory. So first we'll see what is continental drift theory. Wegener's continental drift theory talks about rifting and drifting of the continents, which has given rise to present-day arrangement of continents as well as changes in the climatic regions of the world. So in ancient time, what happened? That time this our Earth was first Earth was made up of a full supercontinent that was known as Pangea, and there was a super ocean that was known as Panthalassa. So that what happened, that Pangea, due to the continental drift, you see inside the Earth there is lot of heat, and so Earth crust is interior Earth is made up of mantle, crust, and core. So that mantle is it is in magma, and that crust is in solid state. So that is solid crust. So what happened due to the heating of the Earth crust? During that time, we had the satellite, that is moon, our Earth moon. What happened? That moon force, gravitational force from the moon, and centrifugal force from the Earth, that led to the bombardment of this Pangea, super ocean Pangea. So that led to the northward and southward movement of Pangea supercontinent. So that led to the formation of northward movement. That northward continent was known as Laurasia or Angara land, and southward continent was known as Gondwana land. So see, first that earth was like here. See, first it was like in fully joint shape in Permian period. So what happened in Carboniferous before the Carboniferous period? That time Earth was fully joined. Then after Carboniferous period, Earth started separating. That supercontinent, that Pangea, started separating due to the tidal force. See here we will study about the forces behind the drifting of continents. So in this what happened, that equator was due to interaction of forces of gravity. So due to the gravitational force of moon, so gravitational force that it was pulling the earth, and then from earth centrifugal force. So centrifugal force is what? Earth is that supercontinent, that Pangea is fully bulged. So from here centrifugal force is putting outward force, that is pole fling force. So putting the outward force, so that led to the separation of that two parts, that is Laurasia and another one is Gondwana land. So that is due to the gravitational force and polar fling force, that is due to centrifugal force caused by Earth's rotation and also buoyancy force. So if the force responsible for the division of continents, division of supercontinent Pangea, that is gravitational force, and polar fling force, that is a centrifugal force of Earth, and buoyancy force. And then one more tidal force that due to the rotation of Earth and Moon, because the Earth's motion. See, westward due to the tidal currents because of Earth's motion. Earth rotates from west to east. So tidal currents act from west to east to west according to weather. So due to the tidal force of Sun and Moon, so that was also one case for the separation of supercontinent Pangea. So that led to the separation of supercontinent Pangea into Angara land, and one more is Gondwana land. So Angara land that moved to here. Okay, this one is Gondwana land. Here this part is Gondwana land, and this part is Angara land. So that in Jurassic period that separated. So this one is Angara land and this one is Gondwana land. So this Angara land is also known as Laurasia. So this Laurasia, after in a Paleogene period, that divided into North America and Eurasia. That is Eurasia. So Europe and Asia, some parts of Asia. So North America, Laurasia or Angara land in Paleogene period separated into North America and Eurasia, and while the Gondwana land separated into South America, Africa, then here it is Antarctica, this is Australia, and this is our country India. So after slowly it started moving to the northwest, and then finally now in present day our this whole world map is like this. And so this is North America, this is South America, and this is Africa. Here we have India, Australia, and this is Europe and Asia. So now in present day we have this continents. So that was due to the force of gravitational force, then centrifugal force of Earth and buoyancy force, and also the tidal force of Sun and Moon acting on the Earth. So see here, better you can understand here. See, and yes, that while that acting of gravitational force, centrifugal force, and buoyancy force, that led to the open up of a sea that is known as Tethys Sea. So that led to the open up of Tethys Sea. Then after that in Paleogene period, it started separating, and Quaternary period it is like this. So you can see in Paleogene period, that was in Carboniferous period, this Earth was like this. Our supercontinent Pangea is fully solid crust. Then it was surrounded by an ocean, that is Panthalassa. Then after it in Mesozoic period, that Earth solid crust supercontinent Pangea divided into two parts, that is northern part is Laurasia or Angara land, and then the southern part is Gondwana land, and that led to the opening of Tethys C. Now in the Cenozoic period, so that led to the opening of North America, Eurasia, South America, Africa, India, Australia, Antarctica, and Madagascar. So now that led to the opening of the all continents. Okay. So see, first now we will study about the continental drift theory was proposed by Alfred Wegener in 1912, and it was first put forward by Abraham Ortelius in 1596 before fully being developed by Alfred Wegener. So the theory deals with the distribution of the ocean and the continents. According to Wegener's continental drift theory, all the continents were one single continental mass, that is supercontinent named as Pangaea, and mega ocean, that is super ocean, that was known as Panthalassa. So although Wegener's initial theory did not cover mantle convection until Arthur Holmes later proposed the theory. So in the later part we will study about the convectional current theory also. First we will see, okay. Then supercontinent was named as Pangaea and mega ocean was named as Panthalassa. So now we see Pangaea first split into two big continental masses known as Gondwana land and Laurasia. Laurasia was moving northward and Gondwana land was moving southward. Then later Gondwana land and Laurasia continued to break into several smaller continents that exist today. So see, now by seeing this diagram, I have brought this much diagram for you to make you to understand. So see, here Tethys got the opening after the force acting on the solid crust, that is supercontinent Pangaea. So that led to the opening of Tethys Sea and they led to the separation of Laurasia and Gondwana land. That led to opening Laurasia and Gondwana land. Then after that, it led to the, in Mesozoic period, it led to the opening of in Cenozoic period, it led to the opening of all the continents on the earth crust. That was due to the plate tectonic movements. Okay, if question comes, what are the forces responsible for the continental drift of the continents? So that is gravitational force, then centrifugal force of the earth and buoyancy force, and also the tidal force of sun and moon. Okay. Now we will see about the centrifugal force, that is polar cleaning force, relates to the rotation of the earth. Earth is not a perfect sphere, but it has a bulge at equator, and if we go at a pole, that is not that much bulge. This bulge is due to the rotation of the earth. So greater centrifugal force at the equator. So centrifugal force increases as we move from poles towards the equator. This increase in centrifugal force has led to the polar cleaning according to the Wegener. Then tidal force is due to the attraction of moon and the sun that develops tides in the oceanic water. So according to Wegener, these forces would become effective when applied over many billions years and the drift is continuing. So still now drift is going on. In later stage we will study about this ocean, Pacific Ocean, Atlantic Ocean, Indian Ocean. So in that we will see still now how much drift is going on, and after how much this Atlantic Ocean is expanding, how much Pacific Ocean is expanding per year. So that also we will see. So this was the forces. This was the force behind the drifting of continents. Now we will see. See, if he has given theory, then he has to give some evidence also. Otherwise, without evidence, he can't give this theory. So he had found some evidence that we'll see now. So first evidence was the matching of continents, that is jigsaw fit. See here. One is apparent affinity of physical features, so that matching of continents. Then another evidence is botanical evidence. Then another is placer deposits, tillite deposits. That tillite deposit also known as glacial till. So that is tillite deposit. Then polar wandering, distribution of fossils, rocks of same age across the oceans. See, first we'll see about the apparent affinity of physical features. See, apparent affinity of physical features. See, first when our full supercontinent was Pangaea, it was like this. When it started separating, Then that South America became separate, Africa became separate. Like this in this map or in this world map, you can see. So what happened through this world map? You can see. You can find this part of here. If you try to fix this part here, then this will become one part. Then this part you can fix it here. Then this part, if you fix it here, see here in this, you can see this part is fixed in South America, part is fixed in Africa. Then here India is closer to here is Madagascar. Then here is India. So that is also attached to Africa. Then Australia. See, Australia now in present we have here, but Australia also joined when in the Carboniferous period. That time it was like this. So that all mountains found in this, like see South America, if we find the mountains ranges in the western side and in the eastern side of Africa, that mountain ranges are of same age, same rock. So by these evidence, he concluded the theory, drifting theory. So see, the bulge of Brazil, South America seems to fit into the Gulf of Guinea, that is Africa. So here is Brazil, that is seems to fit into the Gulf of Guinea in Africa. Then Greenland seems to fit in well with Ellesmere and Baffin Island of Canada. So that Greenland is here. Yeah, Greenland is here. So that when after separating, that when this side that became North America. So that Baffin Island of Canada and Ellesmere, that seems to be in fit. Then the west coast of India, and India, Madagascar and Africa seem to have been joined. So this India, Madagascar and this Africa seems to have joined. So and after North and South America as one side and Africa and Europe on the other fit along with the mid-Atlantic region. So see here if we see the map, here we have the mid-Atlantic region. This is South America. This is this is South America, and here in middle we have Atlantic region that is spreaded through all these parts. So these parts, this here North America and South America one on one side and Africa and Europe on other fit along the mid-Atlantic region. So if mid-Atlantic region was not there, then that will be fitting equally. So due to the forces, all those forces acting on the supercontinent, that led to the separation of Earth, and so that evident we are finding in the South America also that rocks of same age, and also we are finding rocks of same age in the Africa side also. So this was the first evidence. Then second evidence is this first evidence was the jigsaw fit of continents. So that was the fitting, and then second evidence was the rocks of same age. So the rocks of same age, see here, this is Caledonian and Hercynian mountains of Europe, and this is Appalachian of the USA. So that seems to be one continuous series. So rocks of same age types are found across Atlantic Ocean. The mountains of Appalachian, Ireland, and Scandinavian countries are similar. So this is possible only if the continents were together. So the rocks of same age we found that across the ocean. So due to that also, that evidence also gave the continental drift theory. So the belt of ancient rocks of 2000 million years from Brazil coast matches with those with Western Africa. So here that rocks of Brazil that matches with the west coast of Africa. So that led to the led for the evidence of continental drift theory. Okay. Now we'll see the third evidence, that is tillite deposits, that is glacial till. See what was happening when Earth was separating, when that supercontinent Pangea was separating. That time what happened? There were frictional force. So due to that frictional force, it was moving. That after that separation, this Antarctica it went down. So that was when it was joined. So that was due to a frictional force. Some tills, that some glacial landforms can be found in this south of South America, then in South Africa also, then India side also. So through that was also evidence for the continental drift theory. So see, this is tropical country. Even our country, India, is also tropical country. So that will be hot. So here it will be not possible to find glaciers, but we are finding glaciers. That is that they are the remains of the glacial deposits that due to the frictional force when it was separating. So these evidence we are finding it here. So that is also the evidence for the continental drift. So evidence of glaciation in Brazil, Africa, Peninsular India, Australia that are found. So tillite deposits, that are sedimentary rocks formed out of deposits of glaciers. The Gondwana system of sediments are found in India, Africa, and Falkland Island, Madagascar, Antarctica, and Australia. All were previously part of Gondwana. So overall resemblance demonstrate that these land masses had remarkably similar histories. So this was the evidence of continental drift. Now another evidence we will study, that is botanical evidence. So in botanical evidence, see here, that time in Mesozoic era, when we had that dinosaurs era, Jurassic era, Triassic era, and Jurassic. Okay, sorry for inconvenience. Okay, see, being that in Jurassic period, Triassic period, so that time there were many animals found. So their fossils are found in some continents, some countries also. So see here, presence of Glossopteris vegetation. This is a tree. This is a tree in Carboniferous rocks of India, Australia, South Africa, Falkland Island, overseas territory of UK, Antarctica, etc. So same land was called Gondwana. So this from the Gondwana land, all this in Carboniferous period, all this they were together. So they were the part of Gondwana land. So this Glossopteris vegetation that can be seen in all these continents. So that also is the evidence of continental drift. So see, here is this fossil remains of the freshwater reptile Mesosaurus. So see here, Mesosaurus we are seeing in South America, and also Mesosaurus is found in South America also. So this Mesosaurus is a freshwater animal. So here now our continent has opened up. So here we have the Atlantic Ocean in middle of this. So Atlantic Ocean, that is marine water, that is salty, but whereas this animal is fresh water. So and we are finding this particular animal is in South America also, and also in South Africa. So by these evidence also we can say that this part was joined. That's why after separating, some animals came to the South America side and some animals came to the South Africa side. So fossil remains of the freshwater reptile Mesosaurus. Then fossils of the fern Glossopteris. This is Glossopteris is a flower. So found in all of the southern land masses. So here you see Glossopteris that we are finding it is in South America also, South Africa also we are finding. Then we have in India also, that is in southern India. Then we have in Antarctica and also in Australia. So by this also we can say that in a Carboniferous period that continent was joined. Then similarly we can see about the fossils remains of the Cyanothea of sorry, this is not properly visible. Okay. Then fossils remains of this animal, that is Lastosaurus, that is also in Africa, India, and Antarctica. So by these evidence we can say that in Carboniferous period, all these continents were one part, that is part of Pangea supercontinent. Okay. So now next we'll see about the placer deposits. So that placer deposit means you must know that placer deposits are found in the in placer deposits gold are found. So if anywhere gold comes, question comes, and that is about placer deposits, so mark the placer deposit. So rich placer deposits of gold are found in the Ghana coast of West Africa, but the source gold bearing veins are in the Brazil, and it is obvious that the gold deposits of Ghana are derived from the Brazil plateau when the two continents lay side by side. See here. But now all these fossils or all these remains we are seeing on the earth, that is due to the volcanism. So that's okay. So see here. Here in Africa, we are finding the deposits of, in that Ghana coast of Africa, we are finding the deposits of gold, but we are not finding the source from where that would have come due to the volcanism only. After that, when volcano took place, that time all those materials after solidifying, after cooling, and then after when it became solid, that became for the deposits of gold. So for that we should find source also. But we are in Africa side, we are only finding the deposits of gold, but we don't have the source from where that all that gold deposits came. But that source, that gold deposit source, that vent is there in the South America region, that is in the Brazil side. So in that South America region, that vent is there. So from where that volcano erupted, and that led to the deposits of gold in Africa. So from these evidence, that also we can conclude that this once upon a time, this both South America and Africa was one of the same part, and after that separation, that separated after opening of Tethys Sea, and after the drifting, that led to the separation of both parts. So from these also we can conclude that this led to the continental drift. So this is also the evidence of continental drift. So see here, source is found in this area of gold deposits, but where that deposits is found is in Africa side. So this is also the evidence. Okay, now we'll study that all the matching of continents, that is jigsaw feet. So that coastline of South America and Africa fronting each other have a remarkable and unique match. So that jigsaw feet, you can say that fitting, that jigsaw feet. So this, if we fit, this is known as jigsaw feet. So this is the first evidence. Then second evidence is rocks of the same age across the oceans. So rocks of the same age across the ocean, we have seen the radiometric dating methods have helped in correlating the formation of rocks present in different continents across the ocean. The ancient rocks built on the west coast of Brazil match with those found in Western Africa. So this is the evidence, second evidence. Then we have the evidence of tillate, that glacial till. So that is the sedimentary rock made from the glacial deposits. The Gondwana system of sediments from India is recognized as having its counterparts in 6 different land masses in the southern hemisphere. So that is Madagascar, Africa, Antarctica, Falkland Island, Australia. At the base, the system has thick tillite signifying widespread and sustained glaciation. So that tillite deposits also the evidence of continental drift. Then we have the placer deposits that we have seen that this source is found in the South America, and whereas the deposits is found in the Africa region. Then distribution of fossils, that glossio fossils, then Mesoceras we have seen. So this was also the source for the evidence for the continental drift. So all these were the evidence of continental drift. So see, continental, even that continental drift was given, after it he was criticized by some people, and there were some drawbacks of continental drift theory. First, he did not explain about how that movement took place, because that tidal forces of the moon, tidal force and gravitational force, they were not that much strong. They were to move the continents. So see, Wegener failed to explain why the drift began only in Mesozoic era and not before. So why that drift began only in Mesozoic era, not before? The theory does not consider oceans. Proofs heavily depend on assumptions that are generalistic. forces like buoyancy, tidal, and gravity are too weak to be able to move the continents. So that gravitational force, tidal force, they were not that much strong to move the continents. So how come that continents are moved? He did not explain that if he could have given that tidal force, if he could have given some that magnitude or something, then he could have explained that that was that strong to reach the continent. But he did not explain about that one. So modern theory plate tectonics accept the existence of Pangea and related land masses, but give a very different expression to the causes of drift. So in that plate tectonics, we'll study about the causes of drift. So this was the drawbacks of continental drift theory. And then finally, even though it was not that much approved, but it led to a strong foundation for the future, the theory like seafloor spreading and plate tectonics. So this is the end of continental drift theory. So now we have finished the continental drift theory. So in continental drift theory, you must know about that Pangea, then Panthalassa Ocean, then you must know about the Angara land and Gondwana land. That Angara land also known as Laurasia. Then during which period they started drifting, and during which that in Jurassic period, like it was separating. Then in Paleogene period, it separated and became that continents. So, like you must know about all this and about Tethys Ocean, Tethys Sea. So that everything and evidence. Evidence also you must know that evidence. See, all these evidence will be seeing in these further parts, because see all these evidence you will be studying like all that mountain ranges and everything. So that will be useful there. So that there you can say that at some point even Alfred Wegener was also correct. But only thing was that he was not able to express about that forces magnitude. So okay, continental drift theory we have finished. Any doubt in this continental drift theory? Anyone? Any doubt in continental drift theory? Any doubt in continental drift theory? Anyone tell me? Okay. So now we have finished about the continental drift theory. Now we'll see convectional current theory, seafloor spreading theory, then paleomagnetism. Then after that, tomorrow we'll see about the plate tectonic theory. Then we'll study about all plates and everything. And then after that, we'll see the formation of mountains and everything. So okay, see here. What is convectional current theory? See, convection is what? See here. In the Carboniferous period, what happened? That earth crust, if you see the interior of the earth, we have the first upper part, that solid crust, that is crust. Then we have lower of the crust, we have mantle. Then we have core. So see, this is crust, this is mantle, and this is core. So that this outer part of mantle and this crust, that is known as lithosphere. So here, convectional current theory was proposed by Arthur Holmes. So that was proposed in 1928, 29. Somewhere you might find it like 1930. So don't get confused. It is 1928. So see here, this mantle part, what is, see, this upper part, that crust, that is solid. That is a continent, that is fully solid. And this mantle, what is there, that is liquid in a state. So here what is happening, a high temperature is there inside the interior of the earth. A high temperature is there, and because of that high temperature, that is in liquid state. And here what is happening, see here, what is mean convection? Convection is, suppose if we heat water, suppose you take, this is the temperature, sorry, suppose you take, this is the temperature, high temperature, and this is a liquid, and mantle is in liquid state, and this you can take it as water. So if we heat that water, that will start flowing, and that will start becoming into vapor. So after becoming vapor, that will change, that will go up, and again after it will fall down. So that will be the convection. So that will be the convection. So that convection current we will study here in the earth crust. So see here what is happening, this mantle is fully liquid in state and it has high temperature. So due to high temperature, what is happening, this here some parts will what will happen, they'll try to escape. So they'll means what they will try to evaporate, means they want to become vapor. But in that case, what will happen, since this crust is fully solid, so they were not able to go out from this place. So what is happening here, that some stronger, if that a stronger temperature that providing from the mantle, then this will lead to the formation of volcanoes, and other parts where temperature is less, then that will converge. So sorry, that will diverge. This here current will what will happen, that will diverge. So again, if it will diverge, so here also crust is there, solid materials is there. So then it will become in a circular state. So what will happen? See here, suppose this is the continental crust, and this is mantle. So this in this mantle, what is happening? That liquid state, what is happening? That high temperature in the volcano area, that is trying to escape from this mantle surface. So it is trying to become vapor, that is trying to go to the crust area. So that will lead to the volcano, that process of volcano. So in that volcanism, what will happen? That once it erupts, so in that what will happen, that will lead to the formation of land mass. See, first it will, that magma will come off of the earth, then after solidifying, cooling, it will become solid, then that will lead to the formation of some land mass. So that land mass is known as mid-oceanic ridge. So in that ancient era, that Tethys Sea or that ocean will see that erupted. So in that Atlantic Ocean, we'll see the mid-oceanic ridge. So that is due to the process of this volcano only, volcanism. So this here, what will happen, that convectional current, they'll start flowing. So this will lead to the process of volcanism. And what will happen, this will diverge. So once they'll start diverging, then again it will become here in circle, then again it will be going on. So here, this side also same, then this side also same. Again the same process will be going here on here also. So this one is known as rising limb. See, this one is known as rising limb. So here diversion is taking place. Then after it, again in the some other parts, again same, that diversion process will be taking place. And then that diversion place, again it will meet in the here this falling limbs. This one is falling limbs. These both are falling limbs. So again they will meet in this area. So here they are converging. So here in this converging area, what will happen? Here in converging area, we find the fold mountains that lead to the formation of fold mountains, and here it will lead to the formation of ridges, that big mountains. So that will be not fold mountains, that will be big ridges. So this one is rising limb, and this is falling limb. And in this, see, in diverging boundary, what happens? We find the constructive plate boundary. In diverging boundary, we find the constructive. So see here, construction is going on. That some land mass is created. But whereas here in this place, what will happen? This is converging. So here destructive boundary will find. So here whole mountains will take place. Suppose see, now we are on the crust, and now we can take this as continental crust and this as oceanic crust. So what will happen? Oceanic crust is more denser, and whereas continental crust is less denser than the oceanic crust. So what happens? This oceanic crust is more denser, so this will start going down, and this will start going up, that continental crust. So that will lead to the formation of trenches. That deep will find the trenches that will see here is some other part. So that will lead to the trenches, that is due to the convergence, and this destruction means we'll find the constructive plate boundary. So that will lead to the formation of some land mass. So similarly here we have the mid-oceanic ridge. So see here, convection current theory forms the basis of seafloor spreading theory and plate tectonic theory. It explains the force behind the plate movements. So see here we have the divergence, and then we have the convectional current, Here flowing again, coming, then again it will keep on flowing. See, here in Earth we have the high temperature. So that was explained by the Arthur Holmes. And while explaining, main aim was to explain about the origin of whole mountains and origin of volcanism. So this was his main aim. So in his theory, convection and current theory, he explained about the origin of whole mountains and volcanism that is due to the high temperature in the mantle area. So you see here. Convectional current theory was given by Arthur Holmes in 1930. It discussed the possibility of convection currents operating in mantle portion. These currents are generated due to radioactive elements causing thermal differences in the mantle portion. See here. Here also we have the radioactive elements, and also in the Earth's crust, this continental crust also we have the radioactive elements. But here in mantle area, what is happening? That radioactive elements are in liquid state, so they are providing huge amount of temperature. And here in this continental crust, we have that radioactive elements in solid state. That is due to that they have cooled down, so they are in solid state. So that radioactive elements in the mantle area, what is happening? That due to high temperature, it is trying to escape from the mantle area. So that leads to the process of volcanism. And then if they are not able to escape, then again in the circular way they starts coming, then again it will go. So that leads to the convectional current. So this was the main convectional current. So then that leads to a divergence. Again, that falling limbs leads to the convergence. So that they lead to the formation of whole mountains, and while in the divergence will lead to the formation of land masses, that is like mid-oceanic ridges. See here through this also you can understand. See here, this is outer core, inner core. Here it is mantle. Then we have the crust. So see here, this current, that high temperature is going from the both side, then it is trying to escape, but only some parts are able to escape. So that will lead to a process of volcanism, and then again after it will become a circular array. Then again in all places it will be happening at the same time. So that will lead to the formation of ridges and trenches or whole mountains in the convergence area. So convectional current theory is the soul of seafloor spreading theory. Arthur Holmes in 1930 discussed the possibility of convection current in the mantle area. These currents are generated due to radioactive elements causing thermal differences in the mantle. So see here, this upper layer, this continental crust is made up of CR, and lower layer, call it as substratum, that is made up of SIMA, that is silicon and magnesium. So this density of this continental crust is 2.7 gram per centimeter cube. Whereas density of mantle is, that SIMA is 3.0 gram per centimeter cube. So this is more denser. So it will try to subduct under the continental crust. So this is about the convection current theory. So according to this theory, the intense heat generated by radioactive substance in the mantle, that is a distance of 100 kilometers to 2,900 kilometers below the Earth's surface, seeks a path to escape and gives rise to a formation of convection currents in the mantle. Wherever rising limbs of these currents meet, oceanic ridges are formed on the sea floor and due to divergence of lithospheric plates, and wherever the falling limbs meet, that trenches are formed due to the convergence. So the movement of lithospheric plates is caused by the movement of the magma in the mantle. So that lithospheric plates is moved due to the movement of magma in the mantle area. That magma is that hot lava that is in liquid state. So that's all with convection current theory. If any doubt in convection current theory, you can ask. Okay. Now we'll move to the sea floor spreading theory. See, sea floor spreading. This is also one of the main evidence from which this continental drift theory. So from continental drift theory only sea floor spreading theory has been extracted. So see, according to the seafloor spreading theory, the ocean floor behaves like a conveyor belt where it is continuously created along the mid-oceanic ridges while it is destroyed along the trenches. So the rising limbs of convectional current breaks the oceanic crust that cause divergence, and cooling and solidification of magma gives rise to oceanic ridges. So as the ocean floor spreads, new ridges are created along the divergent boundary, while the old ridges are denuded to become part of oceanic crust. So see here we will see what it is. Now you can take this as continental crust, that is land mass. Here what is happening, and this here it is mantle. So here what is happening now, due to that convectional current theory, now that due to volcanism, that leads to the formation of ridges. So now you can take this as ridge. Okay, so if you take this as ridge, when it will start flowing, so after cooling down, that all that materials will flow from here. So flow on the both side. So when it will start flowing this side, so this part they will start cooling down, and this part will become older. Again after some days again if it erupts, then again that lava that will move this side, both side. So this will be in this place only. So this side part will be the older landmass, and whereas here if you find that landmass within that 5 centimeter or 10 centimeter, that landmass will be new landmass. So here in this seafloor spreading, what happened? We saw that rocks of this both side, that 5 centimeter of ridges of both side, they are of same age and they have the same chemical properties. And whereas this rocks of here this oldest landmass, they have the same age. So they are differing from this new landmass to this one. So they have the difference. So from that also we can study that sea is spreading, that landmass is spreading. So this one is older landmass, this one is older landmass, and this one is new landmass. So see here, Harry has proposed the idea of sea floor spreading when oceanic ridges. See, actually what happened during the World War II, sea floor spreading theory by Harry S was proposed in the 1960. So during World War II, what happened? They were trying to attack the enemy through water, through the submarines. So when they went deep inside the ocean, that time what happened? They found that many type of land masses inside that sea or oceans. Like if you'll say that oceanic land masses like trenches, abyssal plain, mounds, geodes. So that land masses were found. So they tried to study about all those land masses. So that led for the concept of sea floor spreading. So for searching for that submarine area, so in that led to the concept of sea floor spreading. So see, Harry has proposed the idea of sea floor spreading. When oceanic plates diverge, tensional stress causes the fractures. So see here, oceanic plates when it is diverging, that leads to the tensional stress that causes fractures to occur in the lithosphere. So that tensional stress that you can see here also, very like that convectional current theory. Here you can see once the current is going up, so here there is a tensional stress, so that lead to the fractures to occur in the lithosphere. So that leads to the formation of ridges. So basaltic magma rises from the fractures and cools on the ocean floor to form a new sea floor. The newly formed sea floor oceanic crust then gradually moves away from the ridge, and its place is taken by an even newer sea floor. So that again it moves, so that here that it is taken place by newer sea floor, and here we can find the older sea floor. And the cycle, and again the same cycle keeps on repeating. So see here. See here. Now in the divergence, we saw that formation of ridges. So similarly in convergence, that we will find the formation of trenches. What will happen? That continental crust. Suppose if you take this as crust and this as oceanic floor, so that oceanic, since oceanic floor is more denser, so it will subduct. When they collide, then that time oceanic floor will subduct, and that will subduct, then that will lead to the deeper part. So that is known as trenches. So here you can see, here this deeper part, that will be more deeper, and that will be not slopey. That will be like, you can say, like just 15 degrees. So it will be the formation of trenches. And see here. So this will be the due to the convergence, that is distatic plate boundary. And this, see here, and around, see, if you take the example of like 200 million years, what happened during that time? That before 200 million years, if you see the land masses of here, this area, that oldest land masses, they were the same age, and these new land masses were the same age. But around 200 million years, we'll find that this was different from the new land mass. So that also led to the concept of sea floor spreading. So even now, today also we'll see that Atlantic Ocean, they are expanding 4 centimeter per year. They are spreading 4 centimeter per year. And whereas Pacific Ocean is spreading 12 to 15 centimeter per year, and Indian Ocean is spreading 3 to 6 centimeter per year. But here in Pacific Ocean, will what happen? Since they have lot of trenches, so in that what is happening? That ocean floor is going down. So in this, don't get confused. This Pacific floor is spreading, but due to the most of the trenches located in the Pacific Ocean, so that is leading to the submergence of Pacific Ocean. So Pacific Oceans, after some times, there will be no Pacific Ocean. So the trenches, see, trenches, they are deeper parts, so they are going down. So that are leading to the submergence. And see, Curie point. Why I brought this Curie point? See, here we have studied about this here. Here we have studied in this, in convectional current. So here in this, that current, that convection current, when it is going up, what is this liquid, this molten liquid in a mantle. So here what is happening in earth crust? What happens? That temperature after solidifying, it cools down. After solidifying, it cools down. So that Curie point is okay. So after, when it cools down, that leads to the polarity of that magnetic field. So in that what will happen? That magnetic field. So that north side might become the south side, and the south side may become the north side. So that we'll study in the paleomagnetism. So first we'll see the Curie point definition. Temperature at which certain magnetic materials undergo a sharp change in their magnetic properties. So here in mantle state, when it is mantle, that time Curie point, that magnetism properties will be not there. But once it solidifies, then that time we can see that magnetic properties in the earth surface. So that is known as Curie point. So that temperature at which certain magnetic materials undergo a sharp change in their magnetic properties. So in the case of rocks and minerals, remnant magnetism appears below the Curie point. So about 570 degrees Celsius for the common magnetic mineral magnetite. So like if that temperature is below 570 degree, then you can find that Curie point of that magnetic properties. But if temperature is more than 570 degree, then we won't find that magnetic properties. Okay. So here we are seeing. Now see, with time older rocks are spread farther away from the spreading zone, while younger rocks will found near to the spreading zone. So sea floor spreading helps to explain continental drift in theory of plate tectonics. So sea floor spreading leads to the explain about the plate tectonics theory. So what are the evidence of sea floor is spreading? So rocks on either side of crest of oceanic ridges having the equidistant location from the crest were found to have the similar properties. So see here, we are seen here that rocks in the mid-oceanic ridges, then either side that rocks within 5 centimeter distance, they have the same age and same chemical properties. So their age and magnetic orientation. Rocks closer to mid-oceanic ridges have normal polarity and are the youngest, and the age of rocks increases as one moves away from the rest. So see here, that polarity properties, that magnetic properties we won't find here in this area, but we can find that magnetic properties in this area. So this is the magnetic polarity of the magnetism. The rocks of oceanic crust near the oceanic ridges are much younger than the rocks of the continental crust. So that oceanic, see, continental crust, that rocks, they are the older rocks, whereas the oceanic crust rocks are the younger one. Now you can see distribution of earthquakes and volcano along the mid-oceanic ridges. So these are the distribution. You know to study everything. Just study this. The normal temperature gradient on the sea floor is 9.4 degree Celsius per 300 meter. But near the ridges it becomes higher, indicating an upwelling of magmatic material from the mantle. That indicates the upwelling of magnetic material from the mantle. So see here, in general foci of the earthquake in the areas of mid-oceanic ridges, area at shallow depth. See, 0 to 70 kilometer. That if it happened that earthquake took place, then that will be shallow depth. And where in the ocean, that deep will be 300 to 700 kilometers. So that will be the deepest. So along the Alpine Himalaya belt as well as the rim of Pacific, the earthquakes are deep-seated ones. So here in Alpine Himalayan Pacific, the earthquakes are deep-seated. So due to that, they have the long height. Means they have the highest height. And where is in this one? Where if you see the mid-oceanic ridges, they are in the shallow depths. When earthquake takes place, then that happens in the shallow depths. So that ridges, they start spreading. They won't be go into the like long height, but they will start spreading and then they'll become a long chain type. So that will lead to the mid-oceanic ranges that you can see the Atlantic Ocean also, Indian Ocean also. You can see in the Pacific Ocean also. So now we have the finished about the seafloor spreading theory. So any doubt in seafloor spreading theory? Okay. Now we'll start with the paleomagnetism. So paleomagnetism, that was given in 1963 by Vince and Matthews. So paleomagnetism is the study of records of Earth's magnetic field with the help of magnetic field recorded in the rocks, sediment or archaeological materials. So here what is happening? See here. Here this is, suppose this is a mid-oceanic ridge. So here we have the newest landmass and here we have the oldest landmass. So here through these examples what we can see here. Suppose if we take this as Earth, that continental crust. So this here is geographical north, geographical south. So this one is fixed. This geographical north and geographical south is fixed point. But whereas magnetic north and magnetic south is not fixed, they might change due to polarity. So they due to polarity, what happens? That north might become south and south might become north. So that might change. But where that geographical north and geographical south is the fixed point. So that we'll see here. Since we have this mid-oceanic ridges, and in the side, both sides of the at the equidistance, we have the newer landmass, and they don't have this polarity. They have the temperature above 570 degrees Celsius. So magnetic properties won't work here. But in the oldest landmass, this here, as you go the distance from the mid-oceanic ridges, we will find the oldest landmass. So here what happens, that this side was south was found and this side north was found. So that was due to the polarity of magnet. So that polarity of magnet can be found only in the solid materials or materials which have the temperature below 570 degree Celsius. So by that also we can study about the, we won't able to study about the magnetic property of this new land masses, but due to polarity we were able to study about the magnetic properties of oldest masses. So this was paleo, this is paleomagnetism. So that is the study of record of Earth's magnetic field with the help of magnetic fields. So we won't find magnetic field in this newer masses, newer land masses, but in older land masses we can find the magnetic field. So we were able to study about this newer land masses. See, basalt contains magnetic minerals, and as the rock is solidifying, these minerals align themselves in the direction of the magnetic field. So this logs in a record where the magnetic field were positioned at that time. So paleomagnetic study of rocks have been demonstrated that orientation of Earth's magnetic field has frequently alternated. So frequently alternated was it has been keep on changing. That north is becoming south and south is becoming north. The polarity of Earth's magnetic field and magnetic field reversal are thus detectable by studying the rocks of different ages. So what are the evidence? So this paleomagnetism, a strong evidence of seafloor spreading and plate tectonics. So paleomagnetism led the revival of continental drift hypothesis. So that drift hypothesis that was criticized, but that paleomagnetism led to the revival of continental drift theory and its transposition into theories of seafloor spreading and plate tectonic. The region that hold the unique record of Earth's magnetic field lie along the mid-oceanic regions where the seafloor is spreading. So after, if you study the paleomagnetic rocks, then either side of oceanic regions, it is found that magnetic properties, due to that magnetic properties, we have the alternate north-south direction. So that they are flipped. So that is due to the paleomagnetism. So hence paleomagnetic rocks on either side of mid-oceanic or submarine regions prove that it's the most important evidence to the concept of seafloor spreading. So magnetic field records also provide information the past location of tectonic plates. So that oldest land masses, they give the information about the past location of tectonic land masses. So see here, this magnetism property, that polarity of magnetism. So here, so it will keep on rotating. So this north might become south. It will keep on alternating. So north will become south and south will become north. See here. So this results in the magnetic stripping where the adjacent rock bands have opposite polarities. So this process refills over and over, giving rise to a series of narrow parallel rocks bands on either side of ridge and alternating pattern of magnetic stripping on the seafloor. So that's all about the paleomagnetism. So we have finished about continental drift theory that given by Alfred Wegener, then convection current theory given by Arthur Holmes. Then we have a study about the seafloor spreading theory given by Harry S. in 1960. Then we have a study about the paleomagnetism that given by Vance and Matthew in 1963. So we have finished all this, and tomorrow, see, if you understand all this, then only you can understand about the plate tectonics. Then after plate tectonics, then you only can understand about the formation of mountains, ridges, all those land masses. So first you must study or you must understand all these four theories. So if any doubt in all these four theories, you can ask me now. Any doubt in this? Anyone, any doubt in this? Okay, no doubt. I'll share the slide in the group. Just give a study one time, do a revision, and tomorrow we'll study about the plate tectonics and important plates and everything, and important mountains. And tomorrow, if possible, can you all can you all have with you that world map that I had shown in the one slide in this continental drift theory? See here. Nice world map can you all have? Because see, important that we will see about the plates and mountains, so that if we mark in this blank world map, then you will be able to recall all those land masses. and all those mountains. So we won't be confused. So tomorrow, please have this world map, and also I'll provide the India map also. I'll give. See, if you could buy from the shop, okay. Otherwise, take the Xerox copy of these world maps and India map. I'll give in the group also. So just take the Xerox copy of this, so that you can mark that important place, then important mountain ranges that they are there, then rivers. So that will be helpful for you to study easily about all those, and we won't get confused. So okay, that's all. We have finished for today. If any doubt, you can ask anyone now. Any doubt, anyone? Okay. So we have finished for today. Tomorrow, please have the world map and also the India map with you, and we will see important plates and plate tectonic theory and the formation of mountains and all. So that's all for today. Now you may leave now. So we are finishing with this one. So okay, thank you. Just go home and just revise one more time. Okay, thank you.